Okay, so welcome back. So now we're going to keep, on our journey of Unit 4, this idea of systems of particles and linear momentum. So this is going to be a short, quick video. There's a couple of example problems that we really want to hit here. This, if you've taken Physics 1, AP Physics 1, this is going to be a review. Or if you've taken even just an on-level conceptual physics class, this is a topic that is hit in those classes as well. This is going to focus around linear momentum, right? So the momentum of a particle or an object that can be modeled as a particle of mass m with a velocity v is defined to be the product of the mass and the velocity of a particle. A simple way to talk about momentum is it's essentially inertia in motion, right? And remember, inertia is mass, motion is speed or velocity. Okay, and so the formula simply becomes m equals m, or p equals mv, right? And so momentum is represented by p. I've been studying physics for over 20 years now. I never really got, I really never had an explanation of why momentum was p, but it actually comes from the word patera, right, which means to impede. Right? And there's your P, right? It has to go back to Latin or Greek roots. I forget if patera is Latin or Greek. The way I've always explained it to my students is, look, there's an M here. Why would you do two M's in the same equation? Okay. Now, the SI unit for momentum is simply the unit of mass times the unit of velocity. Sometimes if you're doing a conservational momentum question, you can leave your kilograms in grams as long as everything's in grams, because they're kind of like ratio type stuff, and so you end up canceling out masses. But if we look at the relationships, because remember, multiple choice questions, they do like these relationships. So P, right, momentum is directly proportional to the mass. So the bigger the object, the more momentum it has. It is also directly proportional to velocity, right? So the more velocity, the more momentum. But notice that mass and velocity are inverses of each other, right? To keep the same momentum, if I have a larger mass, I would have a smaller velocity and so forth. Okay, so basically, again, remember, if V goes up, P goes up. If get a different color, because yellow sometimes is hard to see. If M goes up, P goes up, right? But if if V goes down, that means, and I'm going to keep the same P, my M will go up, right? Because they work opposite each other. All right. Now, so linear momentum is a vector quantity, all right, which means it also has components, but remember, we also have to account for the direction. And this is important when you do conservation of momentum, especially if two objects are heading towards each other. It's also rebound type questions where this applies, right? So if I'm going in and I rebound off a wall or a floor, right, my velocity is positive going in, but it's negative coming out. Okay, and so essentially you can rewrite the momentum equation, right, for components. So it's like Py equals m, right, because the mass is going to be the same. Px equals mvx, Py equals mvy, and then you can combine them in various ways by saying P is simply the sum, the vector sum of these two. But how do we find vector sum? Right, we can find the magnitude by simply doing, actually, let's write it like this. Right, so P, you can write it in this form would be like px I hat plus py j hat, right? That vector, that component notation type, which means then you can, right, these are right angles, so you can do Pythagorean theorem. Okay, so momentum is special in the sense that it's only one of three quantities in mechanics that is actually conserved. The other two are mechanical energy, which we talked about in Unit 3, and the other one is the other form of momentum, which is angular momentum, which we'll talk about when we do rotation in Unit 5. Okay, so we're going to study this one in more detail. We've already done, right, so this was Unit 3, and this is Unit 5, okay, when we do rotation. So now here's just a couple of quick examples, and looking at kind of how are kinetic energy and momentum related. So a particle of mass m moves with a momentum of magnitude p. Show that the kinetic energy of the particle is k equals p squared over 2m, and then express the magnitude of the particle's momentum in terms of kinetic energy and mass. And so we know that p equals mv, but we also know that kinetic energy is 1/2 mv squared. And so what I'm going to do is solve my momentum equation for v, and then I'm going to plug it in, right? So I'm going to take this here, plug it into v, and then, kind of work things out. So it's going to be 1/2 m times p over m squared. And so that's going to be 1/2 m times p squared over m squared. And this m cancels one of the m's in the denominator, and there it is, p squared over 2m. Okay, so your kinetic energy can be written in that way. All right, and then the next one says express the magnitude of the particle's momentum in terms of kinetic energy and mass. So we're going to kind of do the opposite, right? So I'm going to say k equals p squared over 2m, and then I'm going to solve this for p, right? So first thing I'm going to do is multiply both sides by 2m. And so it's going to be p squared equals 2mk. And then my last step is simply just take the square root of both sides. And so momentum is going to be the square root of 2 times mass times k. And if you kind of go through and do a little bit of more algebra and plug in 1/2 mv squared in for k, you end up with p equals m times v. And so the next question brings in this vector notation, okay? And so this tells us you have a 3 kilogram particle as a mass of, has a velocity of 3 I hat minus 4 j hat meters per second. You want to find the x and y components of momentum, and then find the magnitude and direction of its momentum, right? And so Vx is simply 3 meters per second. Vy is negative 4 meters per second. Okay, and so there's your, right? So when I do find, I can use this to find Px. It's just going to be mass times Vx, and Py is going to be mass times Vy. And so it's just going to be 3 times 3. So it's going to be 9.0 kilograms times meters per second. That's going to be my x component. I apologize. I always think that I'm writing on a piece of paper, so like just making it heavier. Okay, and then I have 3 times negative 4, and so my my y momentum is negative 12.0 kilograms times meters per second, which makes p, right? If I want to write p in, component notation, it's going to be 9.0 I hat minus 12.0 j hat kilograms times meters per second, right? So that's my momentum. Okay. The other way you can think, if you want to write this this vector notation, you can just simply multiply each number here by 3, and that gives you that notation. Now, if I want to find the magnitude, right? Now I do Pythagorean theorem. I'm not going to find velocity. I'm going to find momentum, right? The magnitude is just simply going to be p equals the square root of px squared plus py squared. And so I'm going to do the square root of 9 squared plus negative 12 squared. Okay, ends up being 15 kilograms times meters per second. And then find the angle, because magnitude and direction, right? We go back to our inverse tangent. So it's going to be inverse tangent of y over x, and you end up with 53.1, not meters per second, but 53.1 degrees below positive x, right? And it's below positive x because your x component is positive, your y component is negative, okay? And so there's my magnitude, and there's my direction. Okay, so in the next video, we're going to look at how can we relate this back to this concept called impulse. And impulse is going to be an area where we do bring in more calculus. To me, it's something I really truly enjoy talking about, because this really leads to kind of, if you want relevance, this brings in car safety, it brings in helmet safety, so it brings in those relevant type scenarios. I mean, you've been in a car, you may have ridden a bike, or if you played football, hockey, lacrosse, and baseball, anything that requires a helmet, right? Impulse is the reason why things are very safe. Okay.